Okay, for this video, we're going to talk about some tricks to factoring. They're not really tricks; it's just an understanding about how they're built to begin with. My pardons. I have my dog in here with me, and she and I are barely back on speaking terms, so she might yelp. Anyway, there's roughly five. I mean, it just kind of depends on who you talk to, that sort of thing. But as far as beginning factoring, we're only going to take a look at 5 different situations in this video. They all kind of work the same way, so it's really only 3 different structures. And if we can get the structure down, the rest of it kind of just falls into place. So the first group is it's a pairing, and it's a perfect square trinomial. So just as the name implies, it's formed by multiplying the same 2 binomials together. That's the perfect square part. The trinomial obviously refers to that the result is going to be a 3-termed polynomial. So I'm just going to go ahead and I'm going to create a generic binomial set. Notice that they're both the same. So the AX and the AX, everything's the same. If you've watched my previous videos before, you'll notice that I don't care for the dirty 4-letter F word. And yeah, take a look at some of my other videos. I'll probably explain it in one of those. I hate it. I can't stand it. Anyway, we're going to distribute. So if we distribute all of our terms through the way the distributive property wants, we notice we get a times a for a squared, and then x times x for x squared. Ax times b and b times ax both result in an a times b times x, but there's 2 of them. So this is going to be plus 2abx. And then at the end, we're going to have plus b squared. Yes, we're all aware of your whininess. All right, so if I kind of rework this really quick for the other option, which is subtraction, multiplying that out, you'll notice that the only thing that seems to change is the sign in the central term. All right, so take a look at the structure, not just how you got them, but the structure of what the result is. You're looking at an x squared. Now this could have been x to the 4th, x to the 6th, x to the 8th, any even number for the exponent on x. We're just going to concentrate on the structure of it, and so it's an x squared. The number in front of it, however, is a squared. That a value is for most of the beginning factorings, the a value is going to be some sort of integer, whether it be negative or positive, it doesn't really matter, but it's not going to be 1/2 or something weird like that. It's just going to be an integer. And so if we take a look at this is going to be a perfect square. Same with the back end. The back end is going to be a perfect square. So we can test this. And we're going to test it fairly quickly. That's the beauty of this, is that as a test, it's actually pretty easy to test. All right, so here's an example. 4x squared minus, let's see, is it minus, yeah, minus 4x plus 1. Now, in both situations, the end, or the second sign, let's get it right here, the second sign was always positive. And the reason for that is that the sign on b is always the same. Otherwise, you don't get that perfect square. So you can see this as ax plus b quantity squared. Ax minus b quantity squared. It's that perfect squareness that gives them the same signs both times. If you multiply 2 things with the same sign, you always get a positive. That's the key. So we look at the end. It is positive. That's good. And then we look at the end numbers. And so as I'm taking a look at the 4 that begins it, that lead coefficient, and I look at the 1 at the end, and I ask myself, are they in fact perfect squares? Now for my students, I have them create a perfect square chart as well as a perfect cube chart, and it kind of helps them through this process. If you don't happen to have one, you can certainly take the square root of 4 and the square root of 1 and see if you get a nice integer. If you do, they are in fact perfect squares. It turns out that 4 and 1 are perfect squares, so they fit at least this part of the structure. What we're going to do now is we're going to check this part of the structure. So to do that, we say, okay, well, let's assume that it works, and then we'll be shocked if it doesn't. So let's assume that it works. In that case, then, this should come back to whatever I squared to get a squared, which was 2, goes on the inside. The x follows along. The middle sign, if you notice, the middle sign seems to duplicate whatever this common sign is, and so this one's negative, so it's going to be minus. And then 1 squared is 1. So this is it, and we're going to square that. Rather than going back through and remultiplying it, we know that the ends work. All we have to do is check this inside term. So to do that, you notice that you take the term that's in back and the term that's in front, and you multiply them together. That's this ABX. Then you multiply by 2, or double it. So we're going to multiply 1 and 2 together to get 2, and then we're going to double it to get 4. Is that what we have in here? Yes. This is it then. It's a structure thing. That's all it is. It's a structure thing. It doesn't mean it's not factorable if it doesn't work. It just means you have to try something else. So this is really meant to be like a 10 to 15 second real quick check. Does it fit the structure of this? If yes, perfect. Go ahead and do it. If no, then that's fine. Do something else. So let's try another one here. Let's try something that's not quite, yeah, let's do something that's not quite as forthcoming. X to the 4th plus 10x squared y plus 25y squared. Okay, and again, the exact same process. So we're going through, I've picked them purposely so that there's no common factor, so we don't have to worry about factoring out that. We're just going through and saying, okay, well, now that we've done all of that stuff, what's left? Well, what did we square to get x to the 4th? And it turns out that we squared x squared. There's a 1 in front, an imaginary 1 that sometimes people will put here. 1 squared is 1, and so technically each one of these is going to have a 1 as a lead coefficient. And then we look at the back and we say, well, how did we get a y squared? Well, we must have multiplied y and y. And then we must have multiplied 5 and 5, or squared 5, in order to get that. And then we bring in the middle sign, and we square it. Now, we know that the ends will work. That's how we built this binomial. All we have to do now is check to see that the central term works. So we take, just like our structure says, we take the ends, the ax and the b, the ax, the 1x squared, and the b, which is the 5y, that's where it's placed. And we multiply those together, so we get 5x squared y. And then we double it for 10. Is that what we have here? Yes. This is the answer. That's exactly how this process works. So root, the structure of trying to find out if it works or not is root, the front root, the back root, and then this is the middle sign. And then you square it. And then you check that front root times the back root. Whoops, let's not put that in there. And then times 2 is the middle term. If it is, great. If not, then just do something else. So an example where this fails. This is a very common example that I tend to use in class just because it's kind of easy to work through, but that's x squared plus 10x plus 16. And so if we go through this process, we notice that x squared is a perfect square, and it ends up being x. Then we notice that 16 is a perfect square. We squared 4. We bring in the middle sign of plus, and we square it. And then we go through our process. The structure says we should take the things on the inside, so 4 and x, multiply those, and then double it and get 2. And then we should get the middle term. 4 times x is 4x, double this 8x. That does not match that. This is not the factoring. We can't, this doesn't work all the time. So don't think that this is a surefire way to get the answer every single time. This is, however, factorable. Two numbers that multiply to 16 that add to 10 end up being 2 and 8. Not a perfect square trinomial, but you can still factor it. So if you've gone through my other videos, I have 4 steps. The 4 steps of going through these factoring issues are, first things first, put it in order. And in order, I mean usually in alphabetical order of variables, if you happen to have multiple variables like the x and the y, starting with the highest degree x. Make sure that that decreases throughout. And then if there's anything left, put the y, and then decreasing the rest of the way. But typically, it's going to just be 2 variables and there'll be 3 terms max. So not that big of a deal. But you're going to want to get it in order. So 4, then 2, then none. Okay, that's in order. Then the next thing is you're going to want to factor out the greatest common factor. None of these had a greatest common factor other than 1. That's not always the case. Do that first. It'll make your life a lot easier. The third step are these specials. I tend to call them the specials. And then, of course, I have to sing the song from Lego movies. Everything is awesome. So this is the specials that I check. This is one set of them. There are 3 sets. 2 of them have 2 possibilities for a total of 5. But I check these first because these are nice and easy to check. Then, if all else fails, you factor whatever's left, however you can. If any one of those steps produces a factor separate than what was there to begin with, so if you get a greatest common factor but nothing else, or there's no greatest common factor but there's a special, or there's no greatest common factor or special but there's another way to do it. If any of those are true, then it's factorable, and you need to write the factored version of it. If none of those are true, then and only then is it not factorable. They're technically all factorable, but that just might not be nicely. It might suck to really do it. So that's really it for this. I'm going to make 2 more videos, one on the difference of squares and then one on the sum and difference of cubes. The sum and difference of cubes kind of falls under another theorem, sometimes known as the factoring theorem. It guarantees you a divisor or a factor that exists, but it doesn't tell you necessarily what the answer is going to look like. So I just came up with a little saying to kind of help me through that and remember. All right, stay tuned.